Statistically, the most.
Okay,
failed
everybody, I think I am gonna go ahead and get started. It's 10 o'clock. I am super stoked about what we're gonna talk about today. But that's true every day. My favorite thing about Matsukadb is whatever we happen to be talking about that day. We are right smack dab in the middle of chapter 4. And first, I want to remind you that it's kind of a normal week around here, which means there's a couple of homeworks to work on. One of them is due tonight. I do have office hours most of the time that I'm not in class, especially after 5:30, all the way till 10 o'clock tonight. I should have office hours with a little dinner break in between. So feel free to stop by and ask me questions. I don't know how many homework problems I'm going to do in class today. Depends on how quickly I move through the material I need to cover. But if I don't have a chance to answer the homework questions during class, I do hope that you'll follow up and stop by my office hours before you turn in the homework tonight, if you need help with any of this. There is also another assignment waiting in the wings, which I'm going to need to edit because it's currently way too long. I have like 4 sections listed there. That's not what it's supposed to be. So I'll fix Friday's homework, shape it up for you, and get that updated as well. But anyway, that's all I got for announcements for today. Just the homeworks. That's mainly what we're working on. Let's go back to where we left off on Thursday last week. Can you remember that far back? Well, I did have you watch a 30-minute video over the weekend, so maybe that kind of kept it a little bit in the front of your mind. I want to remind you about what I said in that video real quick here. This is just a really brief recap about one of the things we like to do with spanning sets. Remember, guys, a spanning set, what is it again? It's just a set of vectors that spans the entire vector space, meaning that every vector in the vector space can be built out of, or in other words, as a linear combination of the vectors in that spanning set. That's basically it. And it's a yes or a no, right? I ask you this, I give you some vectors, I give you a vector space, and I say, are those vectors a spanning set for that vector space? And in the video, and also at the end of class last Thursday, I gave you a recipe for how to answer that question. And it's very, very simple. What we do is we take our vectors and we lay them vertically into the columns of this matrix. Now, by the way, before I go any further, putting the vectors into the columns of the matrix sometimes confuses people, because for most of this semester up until now, we've been laying out our matrices row-wise, right? We will take the first equation and put it in the first row, the second equation in the second row, and we do everything row-wise. And now all of a sudden I'm telling you to put the vectors column-wise into the columns. That is true because here we're doing something very different than we were before. When we were building these matrices before, guys, we were writing the equations of a system into the rows of a matrix. In other words, we were putting those coefficients into the rows of a matrix to solve that system. That was the goal back in chapter 2. So every time in chapter 2, when I was building matrices, I was building them row by row, right? One equation per row, and I laid them out. So you have to understand that this is something very different here. We're actually not trying to solve a system of equations at all. We're testing whether these vectors are capable of spanning our vector space. And to do that, my friends, we simply lay these vectors into the columns of this matrix. And we augment this matrix with an arbitrary vector from V. And as I explained last Thursday, and also in that extra video I had you watch, that arbitrary vector will have specific constants in it that you really don't have to keep track of. It's not important to do that. And so what I resorted to doing is just getting rid of these specific constants. And I like to just use these sort of random number symbols into that far right column. And the question you're asking about this matrix, guys, is will it be a consistent or an inconsistent system? The unknowns in this system are actually the constants of the linear combination. So there's a C1, there's a C1 here, and there's a C2 here, all the way up to Cn. Those are the unknowns that you're thinking about when you're asking this question. And the question is, can you solve for those constants? Yes or no, and it just comes down to whether the matrix is consistent or not. Consistency, remember, this goes back to chapter 2, goes back a few weeks. Consistent systems, those are just where you do not have a pivot going all the way into the far right column. If the pivot goes into that far right column where those number symbols are, that's bad. That means that it's inconsistent, and that means no, you do not have a spanning set. Okay, so that's just a quick little recap. Let's practice on these two warm-up examples here. You'll see that it's not that hard to do these things. So decide if S is a spanning set for V. So I've given you a vector space here on number 1. We're just going to take R2, and I've given you a set of vectors here. These are all vectors in R2, and I want to know, is that a spanning set for V? So if I believe my recap here, what I'm going to do for the solution is I'm going to build a matrix, and I'm going to lay these vectors. Notice there's 4 of them. So this is V1, and this one would be V2, and this one is V3, and then here's V4. We have these 4 vectors. We would lay them into the columns of the matrix. So the first column would be V1, which is the 1 and the 0. The second column is the 0 and the 1. The third column would be 2 and 3, and the fourth column would be 8 and 6. And we would augment this matrix with what? With my number symbols. Now you could put X and Y, or you could put A and B, but the point is it doesn't matter what those actual letters are. It's just important to realize that there's some generic form of a vector in that far right column. So we set up this matrix, and then what we have to do is figure out whether the system is consistent or not. That involves bringing it into row echelon form. Well, guess what, guys? I made this a really easy problem. It's already in row echelon form. I don't have to do a single ERO. Based on how the pivots came out, would you say that this is consistent or that it's not consistent? It is definitely consistent, right? Because there's no pivot going into the far right column. So this would be a yes, just that fast. It's just that fast. Okay, so we don't have to do anything else. We don't actually have to solve the system. They're not asking us for that, so we can just call this good. It's just yes or no. Let's take a look at the second one. The second one is a little bit more involved. So for the solution on number 2, I'm going to build my matrix again. Now here's the thing. With this matrix, you have to smear these 4 entries into one single column of your augmented matrix that you're building here. So notice that these numbers, the 1, the 2, the 2, and the 2, they need to be laid out into a single column. And so I'm doing that right here. 1 and 2 and 2 and 2. And then I'm going to take the next vector, which is 1, 3, and 0, and 1, and I'm going to put that into the second column. And then the third matrix is 0 and 1 and 1 and 0. I make that into one single column. Okay, so those are my 3 vectors. I'm going to augment this with some random 2x2 matrix, which I will just denote using number symbol notation. So far, so good? Now, quick comment here. You might wonder, when you're laying out these 4 numbers into the columns of this matrix, do you have to go from the top left all the way down to the bottom right, or is that absolutely critical? The answer is actually no. If I wanted to, for that first column, I could have decided to kind of go backwards and start at the bottom and do 2, 2, 2, 1. And I could have put that in this first column. The important thing is to do it consistently the same way for every one of your vectors. So if you want to go backwards and do 2, 2, 2, 1 here, that's fine. But then here you'd have to go 1, 0, 3, 1. And then 0, 1, 1, 0. So you just have to make sure you're consistent about the order that you do them in. Question? That also does not matter. Great question. If I were to like shift these around, so this is my V1, my V2, and my V3. If I shifted these around into a different order, we would not affect the answer ultimately to the question, yes or no. You'll obviously get a different looking matrix where these columns would basically get shuffled around somehow, but you would still find out that the result would be the same. Great question also. Okay, so I'm gonna be very quick here, guys, about the EROs on this. The first thing I would probably do, I would leave the first row the same. But I would take -2 times the first row and add it to each of the lower rows. So I'll just tell you what you're going to get. In the second row, 0, 1, 1, and number symbol. In the third row, 0, -2, 1, and number symbol. And in the fourth row, 0, -1, 0, and number symbol. Now keep in mind, if you actually wrote out letters where the number symbols are, like if this was an X, Y, Z, W or something, then over here, this would no longer be X, Y, Z, and W. It would be some alphabet soup mix up of those letters. But again, it doesn't matter what you have over there. So I don't need to like stress about what's actually the correct expressions over here. I can just kind of blindly copy those number symbols down as I go along in the far right column. So I've got a couple of pivots here so far. That's looking pretty good. Let me do another step. I'm going to leave the first row the same now. So 1, 1, 0, augmented with my number symbol. I'm going to leave the second row the same. So 0, 1, 1, and number symbol. I'm going to take 2 times the second row and add it to the third row. And we'll still have a number symbol in the far right. So this time it's 0, 0, and 3 and number symbol. And then in the bottom row, I'm just going to add the second row to the fourth row. So this is 0, 0, 1, and number symbol. By the way, guys, this is week 7 of the semester. I think we've reached the point where we don't need to be quite so tedious with the EROs. Notice I'm not even telling you what I'm doing now. I'm just kind of doing it. Feel free to if you're, as long as you're comfortable with that, I'm okay with that at this point. So there's no need to like dwell on those sorts of things. The last thing I'm going to do, guys, is I'm actually going to leave that 3 the way it is. So let's just leave the first row the same. Let's leave the second row the same. And let's even leave the third row the same. And I'll circle it as a pivot again. I'm being a little sloppy in week 7. Technically, a pivot needs to be a 1, but all I really care about is the positions of the pivots. So I'll just leave that as a 3. And what I'm going to do next, guys, is I'm going to take -1/3 times the third row and add it to the bottom row, and we'll get 0, 0, 0. And remember, these number symbols never change. The number symbols never change. You're not like, okay, so things that, you might think, oh, number symbol minus number symbol, that would be equal to 0. No, it's not. Because this is really x minus y, or 3x plus y minus 5x plus y, something like that. So this is not literally subtracting out to 0 here. The beauty of this is you don't have to think about it. You just recopy those number symbols endlessly as you go along. And notice what's happened here, guys, is we have gotten a pivot all the way down, including on that far right column. So what's the answer to this question? No. It's not consistent, right? So this would be a no. So this one is no, because we got a pivot in the far right column. Everybody follow that? It's not a spanning set. So these 3 matrices are not going to be able to build every 2x2 matrix. There will be some 2x2 matrices out there that we cannot write in terms of these 3. That's basically what it says. Okay, you guys with me? Adrian? Yeah.
Would there be like a rare chance? So say instead of the number symbols, we put like X, Y, Z, W.
X, Y, Z, W, sure.
So there would be like a rare chance with the whole bottom row, one that being 0.
That far right column will never be able to be any zeros there. It will only be expressions involving X, Y, Z, and W. So the answer is no, you would not be able to get the entire row to be zeros. By the way, I want to make another comment. People tend to get hung up on rows of zeros in this class. I mean, I'm not talking about you guys. I'm just saying in general, over 20 years of teaching the class, people get hung up on rows of zeros. That's actually not what's important. What's really important are the columns and the pivots. Are there any free variables, or are the pivots going into the far right column or not? Those are really the questions that you want to focus on. A row of zeros is literally worthless information. If I have a row of zeros, so if I had something like this, people get so excited about this, and then I have to remind them, what that row tells you is that 0 times the first variable, which is x, plus 0 times the second variable, plus 0 times the third variable adds up to 0. That's what a row of zeros means. And if you look at this equation, you realize that it tells you absolutely nothing. You do not learn anything about x, y, and z from this equation. This is worthless information. So rows of zeros should not get us too sidetracked. It's not so much about that as it is about where the columns and the pivots are. It's really what you want to focus on. Does this make sense? Okay, I want to go back to this first example for a minute. And we came up with a good outcome here because we had a spanning set, but I want to throw a wrench in this question a little bit. Because I want you to imagine that every time you grab a vector that's part of your set, it costs you $1,000. Okay, your goal is to get a spanning set for V. This one costs me $4,000 because each of those vectors is kind of expensive, but at least it got the job done. Okay, down here we spent $3,000 and we didn't even come up with a spanning set. Right, but on this first example, we spent $4,000 to have our spanning set, and I'm wondering if you think that that would be as cheap as we could go. Or could we have spanned the R2, which is our big vector space? Could we have spanned R2 more cheaply than having those 4 vectors there? Well, if you think about it, guys, what if I went back for a refund and I said, I don't want this vector, 8, 6. If I don't take that vector 8, 6, then when I set up my matrix, then of course I would not have had this column. Would I have had a span? Would that have been a spanning set with just the 3 vectors that are left? Absolutely, because my pivots are still here and here, right? So I've gotten away with $1,000 cheaper than I did before. And in fact, you probably already realized that I actually don't even need this vector. Because if I remove 2, 3, which effectively removes this column, I still have a matrix that has a yes here because my pivots are not going into the far right column. Now I have managed to span R2 with only $2,000. So the goal here is not just to come up with a spanning set for V, but now we're going to talk about trying to get the cheapest possible spanning set for V. And that's kind of the topic of this next section. So I'm going to dive in right here with the concept of linear independence. Actually, it's kind of both things put together, linear dependence and linear independence. So we're going to kind of get this topic going. These are kind of long words to write down, so you'll see me abbreviating them with LI and LD. So linear dependence means LD, linear independence means LI. And I want you kind of right from the very top, I haven't even explained what these words mean yet, but I want you to kind of be thinking of linear independence, LI, in other words, as being a good thing. And if you have linear dependencies around, if things are LD, that's kind of bad. That's not what you want. So in a moment, I'm going to explain that the 4 vectors that we originally started with on this first example would have been LD. They would have been expensive. That would have been bad. But by the time I've removed the 3rd and 4th vectors and I only keep the first 2, those 2 vectors are now going to be Li, which is a good thing. It's cheap. It's still a spanning set, but it's as cheap as possible. So this is kind of the way I like to think about it. Let's write down the definition of what I mean by these terms. So that we can figure out how to address this. So I'm first gonna define what LD means, which is actually the bad thing. I'm gonna start with that first. So a set, and I'll write it out the way I already have been doing, V1 and V2 and dot, 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 up to Vn is LD. It is LD if at least one of the vectors, at least one, could be more than one, but at least one of the vectors can be expressed as a linear combination, of some or all of the others. So if I can write one or more of these vectors as a linear combination of some or all of the others, that's actually a bad thing. And for your first example, I'm just gonna take the vector 8, 6, which was one of the extra vectors over here that we didn't really need to spend $1,000 on. And I'm gonna show you that we can actually write that as 8 times 1, 0 plus 6 times 0, 1. Right, so I've written 8, 6 in terms of the first two vectors. If I can write one of my vectors in terms of some or all of the others, that's actually a bad thing. So this would be V4 being expressed as 8 times V1 plus 6 times V2, right? That's a linear dependent situation. This is a bad situation if this should happen. It doesn't say we have to use all of the vectors. Notice that V3 is never being mentioned here. But if I've written one or more of the vectors in terms of the others, that's kind of a bad thing. Okay, let me give you another example. So I should conclude this example. So this means that V1, V2, V3, and V4, that set is LD. It is LD. I have written one of the vectors in terms of some or all of the others. Right. Okay. Let me give you another example. Let's suppose I give you this question. Is the set, I guess we haven't done any polynomials yet today, so let's make a new example that involves polynomials. So sorry, steal a little space here. Let's take 1, and then let's take 1 plus x, and then let's take 1 plus x squared. And then I'm going to take 1 plus x squared plus x cubed. And then I'm going to take x plus x cubed. I'm going to take those 5 polynomials and I'm going to ask, is that LD? Is that LD? So, we can label these if we want. So for this example, I'll label the first one as V1, the second one is V2, the third one is V3, the fourth one is V4, and the fifth one is V5. I have 5 vectors here, and I'm really asking, is it possible to write at least one of the vectors as a linear combination of the others? Anybody think they might see if there's a way to do it, Holman?
Last vector.
Okay, so you're gonna work on the last vector. So how can you write V5, which is x plus x cubed? How can you write that in terms of the first form?
Well, V1, V4.
Okay, V4.
Plus
Oh, sorry, minus.
Okay, notice guys, if you take V4 minus V3, he's right on target for this. If you take V4 and you subtract V3, you just get X cubed. Right? So take V4 and remove V3 from it, you just get X cubed, and we're not done yet. What else do you need to do? And take V2 minus V1. Exactly. If you take the second vector minus the first vector, you just get X. If you take the fourth vector minus the third vector, you just get X cubed. And when you add them together, you get X plus X cubed. That shows that V5 is expressible as a linear combination of, in this case, all of the other four vectors. So this set is LD. This is also bad. We've spent $5,000 right now, and turns out the way you want to think about it being bad is you didn't need to spend $1,000 on the last vector because you yourself could have made the last vector by just taking the first four and building something out of them. Right? Same thing here, right? I didn't need to spend $1,000 on 8,6 because I've already spent $1,000 on 1, 0, and 0, 1, and I can use those to build 8,6. Don't have to purchase it separately, right? So that's kind of the idea. By the way, if you're wondering what LI is, I should have, does anybody have a little bit of room in their notes to add it right here? All I'm gonna say is, otherwise, we're just gonna squeeze this right here. Otherwise, it is LI. Okay, that's what I meant to write there, and I just forgot to do it. So if my vectors are not LD, then they would be LI. But so far, the first two examples here, right? This one right here is LD, right? And this one right here is also LD. And so that means that they're both kind of bad. We should go back for a refund. We should return one of these vectors. We didn't need to buy it because we could build the vector in terms of the others. Now, you're probably wondering how you're going to just look at a set of vectors and know if they're LI or LD. We want them to be LI because that's a good thing. Holman bailed us out by figuring out that V5 was equal to V4 minus V3 plus V2 minus V1. But what if we hadn't noticed that? Do we have to just get lucky? Do we just have to kind of glance at these vectors to figure it out? That seems a little bit risky because maybe I won't notice. Maybe I'm not just going to notice how to come up with this kind of a linear combination here. So I'm hoping that there's a better way to do it. It turns out that there is. To help us understand what that better way is, I'm going to take both of these linear dependency equations. By the way, these are called, so let me just add this to the notes here, guys. This is called a linear dependency. This is when I actually write the equation that shows how one vector is expressed in terms of the others. But what I'm going to do, and maybe I'll do it in a different color just to make it really stand out, I'm going to subtract everything to one side of the equal sign so that I just have a 0. So in this case, I'm going to actually keep 0 on the left side, and I'm going to rewrite it with V4 being subtracted over to the other side of the equation. So that is also called, I mean, it's the same thing. That's also a linear dependency. You can refer to either one of those equations as the linear dependency. They're basically equivalent to each other. Okay, so that would be what you have. And same thing here. On this example, I'll do the same thing. This time I think I'll bring everything over to the left side. So I'll add V1, then I'll subtract V2, then I'll add V3, then I'll subtract V4, and then I'll add V5, and I'll leave nothing but 0 on the other side of the equation. Okay, and again, this would be called a linear dependency. And it's a bad thing. We don't want linear dependencies because we've spent extra money on a vector that we could have built out of the other vectors that we already had purchased. Okay. So what you probably are noticing here, guys, is that I can kind of look at the linear dependency in terms of an equation that is equal to 0. So in both of these blue boxes, my equation is equal to 0. I'm going to rephrase this definition of linear dependency now in a more user-friendly way. This is not going to be so great the way it's phrased now. The way it's phrased now is, oh, see if you can find one of your vectors that you can write in terms of some or all of the others. Well, that's like have a haphazard guess. Like I have no idea. But Holman just happened to notice that V5, I don't know how he picked V5, but he picked it out of a hat and said, yeah, V5, I can write it in terms of the others. But again, what if we don't just see that off the top of our head, right? What if it's not obvious to us? So to help us sort of attack this in a little bit more sophisticated and procedural manner, I want to rewrite these equations the way they are in the blue boxes. So to do that, I'm going to rephrase, let me come back over here. I'm going to rephrase what linear dependency means in a slightly more user-friendly way. Okay, is everybody doing good so far though? You guys following this? It's a little bit abstract. The definitions are a little bit strange, but we'll get to some very easy procedures here in just a minute. Okay, so let's do this one. I'm going to rephrase what LD means in a way that's more user-friendly. So let me get my camera over here again. All right. So here it is. The set V1, comma, V2, and comma, dot, 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 up to Vn is LD if and only if, and here's what we want to say, guys, there exist constants. And these will be C1, C2, and dot, 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 up to Cn. And now are you ready for the three most important words of this rephrasing? There exist constants C1 through Cn, and here are the most important words, guys, not all 0. There are constants not all 0, such that C1 times V1 plus C2 times V2 plus dot, 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 plus Cn times Vn is equal to 0. So I've moved everything to one side of the equal sign. And the important thing is that the constants are not all 0. So if we look back at our examples that we just wrote down over here, in this example, we can see that my C1 constant would be 8, my C2 constant would be 6, and my C4 constant would be -1. They're not all 0. C3 is 0, but the other constants are not 0. And same thing here, right? In this example, C1 is 1, C2 is -1, C3 is 1, C4 is -1, and C5 is 1. They're not all 0. You see what I mean? Do you sort of see why we need that not all 0 condition? I mean, if your constants are all equal to 0, wouldn't this just be a dumb equation? Then you're saying 0 plus 0 plus 0 plus 0 plus 0 adds up to 0. Well, I knew that a long time ago, right? It's not interesting. It's not interesting to cancel out your vectors by killing them with zeros for all of the scalars. What this is saying, guys, is that for vectors to be LD, you have to be able to get them to cancel out without just putting zeros in front of all of the scalars. In other words, there has to be an interesting way to make these vectors cancel out. This is an interesting way to do it. It's not just being trivial and throwing zeros in front of the terms, right? So that's the way that we can think about LD. And of course, the rephrase of LI is simply going to be the opposite of that. Because Li and LD are completely opposite concepts. So for the Li rephrasing, which I also want to write down, just for completeness here, is that V1, V2, and dot, 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 up to Vn is Li if and only if the only way to get C1 times V1 plus C2 times V2 plus dot, 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 plus Cn times Vn to equal 0 is when C1 and C2 and all of the other constants up to Cn are actually all equal to 0. The only way, so for linear independence, what you're saying is the only way that you can get your vectors to cancel out in a linear combination is by throwing zeros in front of all the terms, which is kind of the trivial solution. It's the trivial way of solving the system, in other words. Exactly. Are you all with me so far? These are just nice ways of rephrasing these concepts. Again, why am I rephrasing them again? I'm rephrasing Li and Ld because I want to come up with a better way of answering questions about whether my vectors are Li or Ld. I don't want to depend on us getting lucky. I don't want us to have to glance at our vectors and just happen to notice how to get them to cancel out. So I'm heading towards that answer. I haven't gotten to it yet. I have to explain why this rephrasing is going to be so favorable for us. Can we go back to the warm-up example, the second warm-up example? I think I'm going to recopy it here. Well, you kind of still see it here, don't you? Actually, you know what? I don't want to erase this. You'll see why in just a second. This is so awesome what's about to happen. So stoked. Let's go back. So I'm going to keep this blue writing for a minute so I don't have to write it down again. But what I'm going to do is I'm going to go back to that original example. Let's just put it up here again. And let's ask ourselves, is the set that has 1, 2, 2, 2, that was our first matrix. And then the second one was 1, 3, 0, and 1. And then my third vector was 0, 1, and 1, and 0. And I'm going to ask, is it Li or Ld? Now, by the way, let me just remind you, these vectors are already kind of not in our good graces. They were not a spanning set for M2 of R. I've spent $3,000 here, but I have not even managed to span my vector space. Let's ask ourselves whether maybe these vectors could at least be good on the Li question. Well, now how would that look? For the solution, what am I going to be looking at? Well, you can see the main question is that when you build linear combinations of those vectors and set them equal to 0, what kind of solutions do you have? Do you have only the trivial solution, or can you make interesting solutions for this system? So I'm going to set this up. I'm going to take C1 times the first vector, 1, 2, 2, 2, plus C2 times the second vector, which is 1, 3, 0, and 1, plus C3 times the third vector, which is 0, 1, and 1, and 0. And I'm going to set this equal to 0, 0, 0, 0. This is nothing more than C1 times V1 plus C2 times V2 plus C3 times V3 equaling 0, right? So again, if you need to kind of view the notation in terms of the original vector notation, we have V1, V2, and V3. We've set up a linear combination of them here. And this is the equation. Now, guys, this time the question is not if it's consistent or not. I know that this is consistent. Guys, just put zeros for all those constants. I promise you it will be a valid equation, right? The issue here is not consistency anymore. The issue here is there any solution other than this trivial one? So let's just try to see if we can solve this. Well, I have a upper left equation. Guys, this may look to you like one equation. It's actually four equations. There's the upper left corner, there's the upper right corner, there's the lower left corner, there's the lower right corner. Check it out. Upper left, I have a C1 times 1 plus a C2 times 1 plus nothing equals nothing. So equals 0, right? And then let's go to the upper right corner. In the upper right corner, I have a 2C1 plus a 3C2 plus a C3 equals to 0. And now I want to do lower left. The lower left corner would be 2C1 and then plus C3 equals 0. And then finally, the lower right corner of my system would be 2C1 plus C2 and then nothing else. Rest of it's all zeros. And so what you end up with is a system of equations. Would you mind if well, what am I going to do with the system? Solve it. Solve it by doing what? Put it into a matrix, right? That's the answer to everything in 250B. Put it into a matrix. I'm going to put this into a matrix. Now watch this, guys. This is going to be really interesting. Here's the matrix. 1, 1, 0, augmented with 0. And then the next row is going to be 2, 3, 1, augmented with 0. The third row is 2, 0, and 1, augmented with 0. And the fourth row is 2, 1, 0, and augmented with 0. Have we seen this matrix anywhere? I wonder. I'm so glad I did not erase my blue writing. This is actually the same matrix that we had over here. The difference was when we were doing this question as a warm-up, we weren't asking about linear independence, we were asking about spanning sets. So when we started off the day, this is how I basically set up the problem. Right, I had my random vector over here, and I was basically, all these zeros were just number symbols instead. Well, now, when I'm answering the LI question, I'm going to be changing those number symbols to zeros. But the EROs, the hard work that you did in blue here to come up with your O echelon form, is actually going to be identical. It's not going to be something you have to redo it again. You can just take this thing and you can just remember that what you actually had. So I'm going to skip all the blue writing and go straight to the row echelon form. 1, 1, 0 augmented with 0. 0, 1, 1 augmented with 0. 0, 0, 3 augmented with 0. And then 0, 0, 0 augmented with 0. I'll circle the pivots again. And that's what you're going to have. Like so. And the question here is not whether a pivot has gone into the far right column. By the way, that'll never happen. If your far right column is all zeros, you would never get a pivot over there. That's not the question. The question now is, how many solutions do you actually have? Do you have just only the trivial solution where all of the constants are 0? Or are there possible ways to make interesting solutions beyond just the trivial one? What do you think here? If I think about my unknowns, does this system, I'm just asking you a question from a month ago, does this system have one solution or infinitely many? It does have one. It does have one, right? Because there's, notice, if there was going to be infinitely many solutions, we would have had to have what? Free variables. We would have had to have free variables. We do not have any free variables here. There's no unpivoted columns. So if I solve this by back substitution, C3 must be 0, and C2 must be 0, and C1 must be 0. And that means Li. That means that my vectors are actually Li, which is a good thing. Okay, it was bad that they did not manage to span M2 of R, but at least we didn't overpay. We spent $3,000 and we could actually not have, if we remove any of these vectors, we're actually going to be losing something. Right? It's actually going to be a bad thing. So in this case, at least we did as cheap as we could to create these vectors. I can't make this vector out of the other two. I can't make this vector out of the other two. I can't make this vector out of the other two. They're totally independent. They are Li from one another. They have no common ground in that sense. Yeah, does that make some sense? By the way, they may not span M2 of R, but they do span something. Every set of vectors will always, I'm going to say something that's going to sound really stupid. Every set of vectors will always span whatever they span. If I build all possible linear combinations of these vectors, then that's what they span, right? And that is a vector space. Because we learned last week, did we not, that any time that we take the span, I'm just scribbling right now, you don't have to write this down. But any time we take the span of anything, we always get a vector space. So this is a vector space, whatever it is. Turns out it's not M2 of R, it's some smaller subspace within M2 of R. And these three matrices, they will in fact be able to span their own span. If you want to think of it that way. So I don't want you to think that these are vectors that can't span anything. They will span the subspace that they create. But they're just not good enough to span the entire M2 of R. That's kind of the point I'm making. Okay. Let's see. By the way, I said that Li is a good thing. Notice we got a row of zeros. Try not to get hung up on rows of zeros. Okay, rows of zeros, everything, oh, that must be a bad thing. No, not necessarily. What's important here, guys, are the pivots and the columns. Every single column has a pivot in it. And so that means that this system has no free variables. No free variables means the vectors are Li. Yeah. Let's do another example. Except this time I'm going to do something a little clever. I'm going to ask a 4-part question now. I'm going to combine the spanning stuff with the Li, LD stuff that we're doing right now. So check this out. Is the set, I'm going to make the matrix 1, 0, 1, 2. I guess I'm doing another 2 by 2 matrix example. That's okay. And then -1, 1, 2, 1. And then the last one is 2, 1, 5, and 7. And now are you ready for the 4 possible choices? Are they a spanning set for M2 of R, Li, both, or neither? Well, let's see if we can talk ourselves through this question. So I'm going to ask whether they're a spanning set and whether they're Li at the same time. I'm going to do them both at the same time. And you know why I can do them both at the same time? We already know why. It's because it's the same matrix that you end up setting up here. So watch what I'm going to do, guys. Watch how I'm going to do this. You're going to love this because it's going to cut your work in half. I didn't used to teach it this way. I made everybody do double the work. Now I got a better way to do it. Just take each matrix and lay it out into the columns, just like we were doing before. So the first vector is 1, 0, 1, 2. I put that in the first column. The second matrix is -1, 1, 2, 1. And the third one is 2, 1, 5, and 7. And I'm going to augment this. Okay, now when I'm doing the span question, I want number symbols there. That's what we learned earlier. But when I'm doing the Li question, as we've just seen in this example, for the Li question, we actually want zeros there. I'm going to do them I'm gonna double my work, or so I'm gonna cut my work in half by doing them both simultaneously. So I'm gonna put kind of number symbol /0 there. Does that sound okay? Number symbol /0, because guys, as I do my EROs with this, the zeros would just stay zeros and the number symbols would just stay number symbols. Nothing would ever change in this far right column, would it? It's just the left side that I'm gonna be playing with. And if you don't mind, I'm going to go ahead and skip the details of the EROs and show you exactly what the row echelon form is. You probably can tell already that the first two rows are already kind of good to go with pivots. So let me just recopy those first two rows. First row stays the same, second row stays the same. And then I'm just gonna tell you, if you do the EROs, my friends, the last two rows will end up completely zeroing. Oops, I'm sorry, this should be number symbol /0 and number symbol /0 going down on the far right column. Okay, so just take my word for it that that's what will happen. Okay. So I've circled two pivots for sure. Just asking you to trust me that I didn't screw up my EROs here. I've got these two pivots for sure. Now, if I'm focusing on the number symbol part of the issue, which is the spanning set piece of it, I would be in trouble right here. Because this number symbol in the third row would be a pivot that's in the far right column with respect to the number symbol, and that is bad news on the spanning set part of it. It's not a spanning set, just like this one was not a spanning set for the same reason. It's not a spanning set for M2 of R. What about Li? So again, my constants are here. And the question for Li is really, do the constants all have to be zero? Or could there be interesting choices for those constants that would make the vectors cancel out? C3, if you notice, C3 does not have a pivot, which means it is a, what's the word I'm looking for? Say it again. Free variable. Thank you before I collapse. Yes, it is a free variable. And because it's a free variable, it means that C3 can be anything. It does not have to be zero. So I can choose my constants, not all zero. In fact, let's do it. Let's actually solve this one out. C3 is going to be T, which is free. And then by back substitution, if I go to the second row here, the second row is actually, what is it actually? It's just the equation C2 plus C3 equals 0. Everybody see that? C2 plus C3 equals 0. Well, that means that C2 is going to be negative T. When you add C2 to C3, it has to become 0. And then what about C1? Well, I have to go to this first row here. C1 minus C2 plus 2C3 is supposed to equal 0. That's what this first row reflects. Well, if I put in T for C3 and I put in negative T for C2, and I now want to solve for C1, what am I going to get? Let's see, this is C1, there's a double negative here, right? C1 plus T plus 2T adds up to 0. That's actually C1 equals negative 3T. All right? So guys, the constants do not have to all be 0 at all, as you can see. So can we actually, the fact that the constants are not all 0, guys, that means these vectors are not Li either. This is a really lousy set of vectors. We spent too much money and we didn't even manage to span the space that the vectors were trying to span. So it's kind of a lose-lose proposition here, okay? The vectors were not a spanning set, which would have been nice. They're not Li, which also would have been nice. So it's really a double whammy on this one. Holman?
For 2x2 matrix, does the number of values have to be 4 and greater?
You're going somewhere that I'm gonna be going to very shortly. Yes, we're actually gonna be able to count how many vectors we have and be able to say something useful about whether those vectors could be Li or whether they could be a spanning set. So I am coming to that. I am coming to that. Yeah. I mean, actually, if you think about it, there would be no way to avoid, okay, I'll let you spend the next 6 hours changing the numbers on these matrices all you want. You can change them anything you want. There would be no way to avoid getting this pivot way over here. At least, well, it might be down here by the time you get down there. But there would be no way to avoid it because, guys, you can only have one pivot per row. And so if you have a pivot here, you could have a pivot here potentially. But you can't avoid a pivot slipping into the far right column. It's because the matrix is tall and skinny. And so you're forced to have a pivot over into that far right column. That's kind of the excellent explanation of what you're saying there. Yeah. By the way, let's actually make a linear dependency here, since we've gone to the trouble of solving for the constants. Can we choose a value for t? I actually want to choose a specific number. And instead of telling you that there's one right answer for t, I'm going to tell you instead that there's actually one wrong answer for t. And as long as you avoid the one bad choice for what t is, you will be able to make your linear dependency. Does anybody want to give me a good choice of t? 42 would be fine. What's maybe a nicer choice? 41. Even better than that. Keep going, keep going. Okay. Anybody want to go lower? Actually, any of those numbers would work. The only bad choice would be 0. If you choose t to be 0, then you're really going to make all of your constants equal to 0, which is not going to demonstrate what you're trying to demonstrate, which is that there's a linear dependency here. The easiest number to pick is probably 1. And if you do that, then you see that C1 is equal to -3, C2 is equal to -1, and C3 is equal to 1. And using those values, then you can write down your linear dependency. So my linear dependency here would be -3 times the first vector, which is 1, 0, 1, 2, plus, actually it's minus because C2 is -1, minus -1, 1, 2, and 1, and then plus 2, 1, 5, and 7, and all of that is going to be 0, 0, 0, and 0. So about 10 minutes ago, I asked you guys, well, how are you going to be able to just see the linear dependency? If I handed you these 3 matrices on a scrap of paper out on the street somewhere, and I said, are they linear dependent or linear independent? Are you going to just look at it and say, oh yeah, I can see that if you take -3 times the first one and subtract the second one and then add the third one, it will cancel out. You probably aren't just going to notice that, right? You don't have to get lucky anymore. You don't have to get lucky. You just have to be willing to go through the process of putting the vectors into these columns, working it through, setting up your free variables, and then using that to plug in numbers that give you the actual equation. So we don't have to just guess anymore. It's not a guess and check game. It's actually now something that we can find these relationships for ourselves. So actually spending $3,000 was too much. Because after all, the third vector could have been made out of the other 2. So we really only needed to purchase the first 2 vectors, then the third one would have been expressible in terms of those first 2. You see how that works? That's kind of what we're saying here. Okay. I like this. I want to make one small remark here. This one is just, well, it's a handy little thing to know that I haven't really stated anything about, which is that in the case of 2 vectors. Okay, so let's just say V1 and V2. This is only good for 2 vectors. So what the remark is that those 2 vectors, V1 and V2, will be Li If and only if. So what I'm about to say is that if you only have two vectors that you're looking at, if you only have two vectors that you're looking at, you will be able to just glance at them and decide if they're Li. You will be able to do that. Namely, these two vectors are Li if and only if they are not scalar multiples of each other. As long as they are not scalar multiples of each other. So that's only valid when you have two vectors. Let me give you an example. Do that right here, and then we'll take a little break. We're just about done with what I want to say about this LILV thing. But, so, just as a quick example here, guys, I could say, for instance, that the set 1, 2, and then 3, 4, I'll make a matrix 1, 2, 3, and 4. And then I make another matrix, which is -5, -10, -15, -20. Well, in this case, you would be able to eyeball it. You can see that the second vector is just -5 times the first vector. So this is LV, and you can even just write down that V2 is -5 times V1. So there's your linear dependency, and it's just kind of obviously true. Okay, so when you have two vectors, you can just test it that way. If one of them is a multiple of the other, don't spend $1,000 on the second one, right? You can make this second one out of the first one very easily. Make sense? But don't, okay, every semester somebody does this, so just don't let it be you, that they try to use this remark on three vectors. And they'll say something like, oh, so as long as I have three vectors that are not scalar multiples of each other, that they would be Li? It's actually not what we're saying. And in fact, so just, this is kind of my warning example. The one to kind of be a little careful about. I could give you three vectors. I'm just going to take 1, 0, 0, 1, and 1, 1. None of these is a scalar multiple of the other, right? In fact, all three of them point in three different directions. So your first vector is pointing on the x-axis, your second vector is pointing on the y-axis, and your third vector is heading off into the first quadrant like that. These are your three vectors, right? So this is V1, V2, and V3. None of them is a scalar multiple of the other. I can't get one of them by just stretching one of the other ones. They're not scalar multiples. However, guys, these vectors are LD. And you can clearly see it. V3 can be expressed as V1 plus V2. So there's your linear dependency right there. So the vectors are LD despite the fact that you don't have any scalar multiples. By the way, if you didn't notice that the third vector was a combination of the first two, no sweat, because we now know how to solve it. We just put the first vector there, we put the second vector there, we put the third vector there. We augment it. If we're checking for Li, we would use zeros here. Well, guess what? Free variable. C3 is free, and so that means LD, right? You do not have to make the constants 0 to solve that system. So super easy, super easy. Am I going too fast? Hope I'm making sense. I just get excited, that's all. I'm trying to be as clear as I can. Let's take a 10-minute break. I'll let you stretch your legs for a few minutes, and then we'll come back, and I want to pick up this conversation a little bit further. So 10 minutes to stretch your legs. Let's make it sound right. You want to go with it? Sweet, sweet, sweet. I'll be back.
Yeah. Hopefully
It'll be. How's it beyond? So. yeah. But I think it's some kind of those. About. Actually, we were one of the whole issues. This is your turn, who's going to do it? This is by your class. You're still in class. Yeah. This is a new teacher.
No, I don't have that one. I have a different one. No, I didn't have one. But, yes.
Get this person. There you go. What are I shoot? Thanks.
Yeah, he tells me this. He says something.
You crazy?
No.
Is he passable?
Yes, I do it.
What do you? That's our highest thing. I don't know our highest. But everyone else got like. Low 50s or low. Most really low 20.
What'd you get?
Better than most people.
Yeah, you should be. There's all like notations on. Spend all that time.
It'll full to you makers. It's literally not like targeting. That's how how you school going. It's okay. You wrote the wrong one. So entire topic. It's like. You were there, his one job. His wrote from -30 to -10, you found the -10 extra, but on the board you're +30, and then the problem is it's heated. So you go from +30 to -7, so already you're. fine. And then you put in the problem, and you're not sure if I can do it, because. You don't have the right temperature, the original equation. Yeah, fine. They didn't give us time for just that part, but. Not the rest of the parts. And he's like, yeah, that's not gonna help you. Right? Anyway, it was already bad. It's just shit. That's all right. And then the last question, yeah, he explained it to me. It's like other kids who seemed pretty smart. We were both just like. Like that was kind of useless, but actually. I don't know how I needed that. You needed that for like certain. I mean, it wasn't implied. It's still less your thing. Just like I don't know thing. So you see. Oh yeah, that's what I did not study on what people are doing.
Either way, I get on mine.
It's so rude, bro.
I don't know if you, I don't know what you ended up talking to, not get up, not study.
I did not say anything. No, I mean, I was just, yeah. Okay. That was a very.
Are you guys all in the same class?
So what, we both had a thermal class
Oh, thermodynamics.
and our like entire class.
So it was a bad exam or something?
Bad.
Sorry, I'm not trying to eavesdrop, I just.
Terrible profession.
Oh, no.
So when I have to go from that to this.
Is that
You're-
is it
you're-
8 AM class?
No,
Oh,
it's like yesterday.
okay.
You're like sunshine and rainbow, and he's like
Oh.
the opposite of that, but I don't know, parts and shark.
Ay, ay, ay.
So he writes up and let's just look at all the fucking good. This was the, okay, this is. He didn't, first of all, he didn't print the first two out, he had read them before. That's how you get it on the capital copy. And then, you know, and then watch it. This one. So, T13. And we went to make the 16 months is TV. You know what you're talking about. I don't know, you did. There wouldn't be anything. What's the high school? I didn't really say 60.
You have to do up 50.
I don't say. Let me explain it. It's the past.
I don't know, that's why I like,
It was only like that in the past, so. We got it.
I don't know, all these wordings, like, you're confusing, instead of rigid, from the volume, like,
He writes it on top. Read that. Try and like. We're all writing for something.
honestly, I feel stupid.
Yeah.
I added 5 valve, like, that's too so long.
I was going to say that. Yes. No one was. That's the mean. And piston moves down. It is that point, that one there. Like that, those points. This already without it. This crazy. Which state do you know? Only 4.5.
But it doesn't make sense.
Yeah, but
It seems like this. This time. Yeah, but like, see, like. Like if you were a B and it's to change, they're gonna change the C. Or you change your E.
He said that when the team start. Because you watch. Yeah, it's just, it's like, it's. It's not.
Dang it, I was supposed to go to my office to get my hair. I'll show you on Thursday. Is that okay?
Or show the ones that come to office out.
Or you can come to office hours, I'll give you like the extended version.
Anyone said it. So.
Absolutely.
It's professor, it's giving an extra credit. Oh, yeah. You can just let you keep it. You can just extra credit.
It was your favorite sci-fi movie. If you put Harry Potter, then it's like
Sci-fi.
Yeah.
I don't think so.
yeah.
Yeah.
What was her well? Well, put any movie that's sci-fi.
But any movie that's not, you know, and I would mark that. That's good.
It's like
I got the right answer.
All right, guys, I think we got most of us back at this point. I hope that everything's making sense. So is everybody kind of getting the drill with this last couple sections? I hand you a bunch of vectors. I'm gonna ask you, are they a spanning set for V? But I'm also gonna ask you, are they the cheapest possible spanning set for V? Are they Li? Or are they both, or are they neither? Right, I could go both ways with that question. Obviously, the best case scenario would be both. You would love to have a spanning set and to be able to confirm that they are Li, which would mean that it's a cheap spanning set. It's the cheapest possible spanning set. When the vectors are both Li and a spanning set, it is the most important definition about vector spaces, which is the idea of a basis. So I'm gonna define that for you right now. So let's put this down. This section that we're gonna talk about right now is really just gonna be putting together the last two sections. 4.4 and 4.5. We're just gonna put them together. So here it is, guys, a basis. A basis for a vector space V is a set S of vectors such that two things are true. First of all, S spans V. And secondly, S is Li. That's it. When I say S spans V, just remember that means, in other words, S is a spanning set for V. Just another way of saying the same thing. But I like to sometimes just abbreviate that and say S spans V. So my vectors need to be a thumbs up on spanning set, and they need to be thumbs up on Li. In other words, they're both a spanning set and Li. Let's take an example. So as an example of this, let's take our vector space to be R3. And let's take our set of vectors S to be the set of 1, 1, 1, comma, and then 2, 0, 6, and then comma, 4, 2, 2. So we'll take these three vectors and let's just check them out. I want to know whether they span V and whether they're Li. And the beautiful thing is, in the first half of our class today, I explained that you can do both of them at the same time. You can test both of these at the same time because all you have to do is remember to lay your vectors down in the columns of a matrix. So the first column is 1, 1, 1. The second column would be 2, 0, and 6. And the third column would be 4, 2, and 2. And then what we've been learning is that we can augment this matrix with 0 / number symbol. So the number symbols, remember, that's the that's the spanning set aspect of it. And the column of zeros over there, that's the linear independence aspect of it. Okay, and we can multitask and figure them both out at the same time. So I can do my EROs here. Let me see, do I really want to do them? How about I just kind of check it again? Is that okay if I'll just ask you to check? I just don't like to dwell on EROs too long because we've been doing that for quite a while. Let me just get straight to the row echelon form. The first row will just stay the same, 1, 2, and 4. We're augmenting that with 0 / number symbol. And then for the second row, if I take the negative of the first row and add it to the second row, I think I get 0, -2, and -2. And again, I really don't need it to be a 1. Pivots, they used to have to be 1s. Now I'm being a little bit sloppy with it and just recognizing that that will be my pivot position. And then take my word for it that when you work this out a little bit further, you will get a 0, 0, and a 1. In that bottom row. So just take my word for that, that's how it's going to shake out. Okay, that is how it's going to shake out. So this is essentially the row echelon form. You can check some of those EROs just to be sure if you want to. But the important thing is I want to draw the conclusion now. Based on this, would you say that these vectors are a spanning set? Spanning set just means consistent. That just means we should not have pivots in the far right column, and we're good on that, right? So this is a spanning set. And would you say that these vectors are Li? Li just meant that there were no free variables. So that the only way to sort of solve the equation involving these vectors would be to put zeros in front of all of the terms. And that's also true. That's also true. We have no free variables. So let's just write this down. No free variables. And that implies Li, and no pivot in far right column. And that implies that it spans V. So it's both. It's both a spanning set and a linearly independent set, so thus S is a basis for R3. It is a basis for R3 for that reason. Another quick comment I'd like to make about this. You notice that the coefficient matrix here is actually a square size matrix in this case. We saw some examples earlier that that was not the case, where we had these tall skinny matrices and we had wide fat matrices. This is just a perfectly square matrix. What's something that you can always do with a square matrix that you don't normally think about doing for other matrices? Taking the determinant. Do you realize that we could have actually taken this determinant, it would have been non-zero. And you can see that because your row echelon form shows this matrix has full rank, right? This is actually an invertible matrix because it has pivots going all the way down the diagonal. If this is, I'm going back to the invertible matrix theorem, some of the theoretical stuff. If this is an invertible matrix, that's a good thing. And now we see even more reasons that it's a good thing. It means that my vectors are Li. It means that they span the vector space. And in fact, they are a basis for R3. So we actually could have just, now I should write this down. We could have simply taken the determinant in this case. Instead of doing those EROs, we could have taken the determinant. Somewhere I wanted to write that down. Where is that in my notes? Oh, it's kind of disappeared. So anyway, in the case where the A is a square matrix, so the coefficient matrix is a square matrix, we can compute the determinant of A. Obviously, you can't do that unless it's a square matrix. But if it's a square matrix, like it was in this problem, and when I say A, guys, I'm just talking about this, right? This is my original matrix A. If that's a square matrix, we can compute the determinant of A, and let's come up here and make this point. S is a basis for V if and only if the determinant of that matrix is not zero. It's another thing about invertible matrices that is a good thing. It's a good thing. So actually, in this case, my vectors are both Li and a spanning set. I should point out, actually, okay, don't change your notes here. I just want you to observe this with me. I will write it in your notes shortly. But let's just say that this had been a zero. Well, that would have meant that the determinant was equal to zero, which is bad. That would have meant the vectors are not a basis. But actually, it's even worse than that. Not only are they not a basis, they actually fail to span R3, and they also fail to be Li. So on that four-part question, are the vectors a spanning set? Are they Li? Are they both? Or are they neither? As soon as we lose the pivot here, we go from both, which is what we said right here. We go from both to neither directly. It's like going straight to jail, basically. It's not a spanning set. It's not Li. Everything goes bad all at once. Yeah, so in this case, it's kind of a both or a neither scenario. Okay, is everybody okay with that? Are there questions on that example? Do you think that this would be the only basis for R3? The only possible set that could span R3 and that would also be Li? Or would we be able to make others? Well, I think I kind of just got done saying that as long as I have a matrix that the determinant is not zero for, then I'm going to have a basis. I bet everybody in this room, we got about 30 people, I bet we could come up with 30 different invertible matrices that are 3 by 3, and that would be 30 different bases. consisting of the columns of that matrix. In fact, so I'll just make this as another remark. A basis for V need not be unique. You can have many of them. So for example, all I have to do is write down something that when I put them in the columns of a matrix, it'll make it invertible. The easiest one that I can think of would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. It doesn't get any more invertible than that. If I think about what the matrix would look like when I lay these vectors out into the columns, take a look at this. You have not just any old square matrix, you actually have so this would be your A matrix here. You actually have an identity matrix, which is as invertible as it gets, right? The determinant of this is just equal to 1. And so this is such a clean, nice basis that it has a name. This is called the standard basis. It is like so natural. This is the standard basis for R3, yeah? That is the standard basis for R3. But gosh, there would be billions of them, right? I mean, like I said, there'd be 30 of them in this room. I could write down, I don't know, 1, 0, 0, 2, 3, 0, and 4, 5, 6. That's also, so this is another basis for R3. Don't believe me? No problem, just put them into the columns of a matrix. First column is 1, 0, 0. Second column is 2, 3, 0. The third column is 4, 5, 6. Build that matrix column by column and ask yourself, what's the determinant of that matrix? It's triangular. It's triangular, and so we learned a while back that the determinant of a triangular matrix is just the product of the diagonal, which in this case would be 18. Not 0. As long as the determinant is not 0, you got another basis. We could go on. We could do this all day long. I could write down 1,000 other bases. Which, of course, is kind of bad news in some ways because it's like, well, I'm not gonna be able to check my answer with the back of the book. Because the back of the book's only gonna have one answer there. And there's lots of right answers, as you can see. But there is one thing, and I'm wondering if anybody knows what it is. There is one thing that every correct basis will have in common with every other correct basis. So this is a basis for R3, so is this, and so is this. They're all different, but there is one thing that they share in common. I'm wondering if anybody would like to throw out what they think that might be.
Square.
That is basically it, but we need to phrase it a little bit more carefully.
N by N.
It becomes a matrix that's a square size. But let's not look at the matrix, just look at the vector, the list of vectors, because that's how it's going to be presented to you. What's something that's the same about this list of vectors as this list of vectors and this list of vectors? And I'm asking a question that a 10-year-old would be able to answer if they didn't even know anything about linear algebra. Just something that's the same about this, and this. Would be? They all have 3 vectors in them. It's just counting 1, 2, 3, 1, 2, 3, and 1, 2, 3. That is true. Every basis for a vector space must contain sort of a perfect, exactly correct number of vectors. And that's called the dimension of the vector space, which is part of this section as well. So let me write that down as well. So just as a remark, every basis for a vector space V must have the same number of vectors. The number of vectors that you're actually looking at. So that's a definition now that we should write down, so we have it thoroughly into the notes. So that's called the dimension. So the dimension of V, which is written dim of V, is the number of vectors in any basis for V. The number of vectors in any basis for V. Exactly. Again, maybe you don't need to take any notes on this quite yet because I'm gonna write it down, but I just want to kind of convince you why there's this threshold number that's so special. Let's go back to maybe the first one we had over there, 111,206. Again, don't need to write this down. I just want you to think with me on this for a second. So here's my setup that I was doing for that first example, the first basis that we wrote down over there. Can you see why it has to be 3 vectors? If there was more than 3 vectors, if I added another vector here, I don't know, 7, 8, 9, something like that. Of course, now I can't use the determinant, but you know what? What's the most number of pivots that you can have if your matrix only has 3 rows? 3. But how many columns do you have? 4. That means at least one of your columns will not be able to have a pivot because you only have 3 pivots and you have more columns than that. And if you have an unpivoted column, so maybe your pivots go like this, right? What would happen? But you now have a free variable. That's a bad thing. That means that the vectors are LD, right? It means that we don't have to choose all of our constants to be equal to 0. And this is too many vectors. We have now spent $4,000 to try to get our basis for R3 when we have known all along that it only takes $3,000 to get a basis for R3, right? So that's what happens if you have too many vectors. If you have too many vectors, you're going down the LD rabbit hole. You don't want that. But it also is bad the other way. What if I lost one of my vectors and this is what I have? Well, now, remember below your pivots when you do your row echelon form, this is not a 0, sorry, that's terrible. Should not have a pivot around a 0. But below a pivot, you must have zeros. Well, guys, if I only have 2 vectors now, you can see what's going to go wrong this time. I don't have enough vectors to span R3 because I'm getting a pivot into that far right column. So guys, this is a very sensitive value. The dimension of your vector space is a specific number. It's got to be exactly right. If I take too many vectors, this is what Holman was asking me earlier. He was asking me, can I just look at how many vectors I have and be able to talk about whether it's going to be a basis or linearly independent or whatever? And yes, this is my point. If I have too many vectors, they are guaranteed to be LD. It's too expensive. If I don't have enough vectors, I'm not going to be able to span my vector space. So if I want to have both of these conditions, I've got to hit that magic number exactly right. What are the magic numbers that we would have? So for R3, the dimension is just 3. That seems reasonable. What about, so now I'm going to ask you to think of some examples we haven't actually done. But what if we were talking about Rn, and n was any number, so it could be R5, R7, R8, R29, whatever. Do you have a guess as to what the dimension of this would be? I think that's a pretty good guess. If you think about it, every vector in Rn would have n slots. So if you want to make a square matrix out of something that has n slots vertically, you're going to need n vectors to fill up the columns into a square matrix. So this is absolutely right. The dimension of Rn. And by the way, guys, you're going to need to memorize these numbers. You have to know these dimensions. let's try another one. Let's talk about the dimension of P n of R. Okay, interesting. I haven't been talking too much about polynomials today, but let's think about this. So we'll fill in the answer in a second. I don't want to just give it to you straight off the top of my head. Let's just remember what Pn of R is. I'm going to kind of sketch it out here. It's just these polynomials. Any polynomials that kind of look like that form. If I write it that way, do you see a sort of a natural spanning set for Pn of R? Or an easy spanning set, maybe what we could call the standard one. I think last week we did, I think I did this example. I did just the one that stops at x cubed. I don't know if you remember, we had a spanning set for this. Do you remember what it was? 1.
1 plus x.
That would be okay, but what's even easier than 1 plus x? Just x, right? And what would be another one? X squared, and the next one? X cubed. Would you guys agree that every cubic polynomial can be built out of these 4? Absolutely. So it is a spanning set. Not only that, if you removed any of them, if you tried to get away cheaper, let's say you got rid of this guy, would this still be a spanning set for P3 of R? Do the cubic polynomials, are they all buildable out of these 3? There's no x squared here anymore. There are definitely cubic polynomials that have x squared in them, yeah? So I need that vector. I can't get rid of it. I actually need the x squared there. And do you remember in my little 30-minute extra video, I showed you how to take these polynomials and you just lay them into the column. So 1 goes in like that, x goes in like that, x squared would go in like that, and x cubed would go in like that. Look at that. A perfect square matrix that's invertible. It's as nice as it gets. So this is the standard basis for P3 of R. So maybe I should, let me actually write that for your notes now. So just on the side here, I'll just make a quick remark. The standard basis, this is the easiest basis for P3 of R would be 1x, x squared, and x cubed. That's the best basis for P3 of R. It's the standard one. It's the obvious one. It's as obvious as this basis right here of R3. Really, really nice vectors. It's clean, easy to do calculations with those vectors, right? And so what is the dimension of P3 of R, if you believe me that this is the standard basis for P3 of R? 4, right? And what do you think it's going to be for Pn of R?
Plus 1.
It's n plus 1. That's exactly it. It is n plus 1. Again, this is not the only basis for P3 of R. Do you remember in my video, I did, I think 1, and then was it 2 plus 3x? And then I did 4 plus 5x plus 6x squared. And then I did 7 plus 8x plus 9x squared plus x cubed. This is another basis for P3 of R. This one, when you put it into the matrix, and I did it in that video, but just to remind you, it came out like this. 7, 8, 9, and 1, right? And in the video, of course, I was augmenting this with those number symbols. Now we know that we don't just want number symbols, we also want to do the zeros. And the pivots are going to be just like that. You have no free variables, but you also have no pivots drifting into the far right column. It is a win-win situation. You spent $4,000, but that's what you had to spend to be able to span P3 of R. And in general, you just tack on a +1 to the size of your polynomial space. Let me write down a couple others that are good to know. I might let you think about these a little bit. If I did the n by n matrices. I will tell you, or maybe you have a guess. Somebody have a guess as to what the dimensions, say, of like M2 of R would be? I wanted to span the 2 by 2 matrices. How many matrices would it take to be able to do that, do you think? To span the 2 by 2 matrices? So a 2 by 2 matrix, just to scribble it up here, looks like this. Question would be, how many matrices would it take to be able to span anything that looks like this form? 4, right? If you bust out the variables on this, you'll actually get 4 vectors. And how is 4 related to 2? In terms of what would it be for the n by n matrices if you were taking a wild guess? What is that?
N times n.
N times n, which is better known as n squared. Yeah, it is actually n squared. So if I was doing 3 by 3 matrices, I would have 9 entries, and there would be 9 basis vectors for the 3 by 3 matrices. The matrices do not have to be square size. So we could do the m by n matrices, and for that one, you would just take m times n. Okay. Guys, there's gonna be some homework problems for Friday. I wanna make your life as easy as I can. There's gonna be some homework problems for Friday. They're gonna give you a vector space. They're gonna give you some vectors, and they're gonna ask you, are they a basis for the vector space? If you know these numbers, then you know how many vectors should be there. So if we're talking about the 2 by 3 matrices, if they hand you some 2 by 3 matrices, they better hand you 6 of them. If they hand you only 5 of them, you know it's not a basis. If they hand you 7 of them, it's not a basis. It has to be this exact right number. And so I need everybody to learn these numbers so that just off the top of your head, you can say, yep, that's too many vectors, or nope, that's not enough vectors, right? So that way you can answer these questions really, really quickly. Okay, let me wrap this up for today. I know I've been talking for a while today, but I want to get this done. So I'm probably not gonna quite get to that. We'll see what I can do about that. I could just make a little video to solve the problems. I don't know, I have to see. But I just wanted to point out this little thing here. Okay. So let's take a quick note on this. So this is just a nice little rubric that we can use. And I actually have a handout on this that I'm going to show you on Thursday. It's in Canvas already. But let's just suppose that I have a vector space whose dimension we already know ahead of time. So it could be one of those. If I give you Rn, or if I give you polynomials, or if I give you matrices, we know what those dimensions are. If I give you that, and then I give you a set S that has V1, V2, up to Vk. So be careful with this notation. This is a Vk this time. And what I want to point out here, if you can on your notes here, guys, let's kind of make 3 columns. I'm gonna make a little chart for you. And I want to look at some scenarios. What if K is bigger than N? What if K is less than N? And then what if K is equal to N? I'd like to look at all of those cases. So this chart will be absolutely worthless if you don't know the dimension of your vector space. So if you don't know what the right dimension is that you're playing with, you won't be able to use this. So make sure you learn those. That's what I'm saying. Now, having said that, though, I have to be careful. Like if I give you a matrix and I give you, say, null space of A. Now we know that that's a vector space. but I'm not gonna know what its dimension is off the top of my head. I will have to actually work out the EROs and figure out, well, how many variables are there to bust out when I do that whole process of writing down the form of the null space. So there are plenty of vector spaces out there that we do not know their dimensions ahead of time. If we don't know their dimensions ahead of time, this chart isn't so helpful. Because this chart is saying, look, if I know my dimension ahead of time and somebody comes along with a set of vectors for me, I want to be able to say something based on how many vectors it is. I've kind of already been hinting at this though, haven't I? If I bring too many vectors, if K is bigger than what the correct dimension is supposed to be, then that's too expensive. In this case, S must be LD. Sorry, I don't want to say it that way. Oh, take that back. I have a better way to say it. S cannot be LI. Cannot. Again, what's the reason? The reason's so easy, guys. You have way too many vectors. You have vectors going to the right forever, and way over here is your zero vector. I promise you, you will have free variables. You must have free variables because there's more columns than rows. We made that point earlier, right? If the matrix is wide and fat, you will have unpivoted columns for sure, which is bad. That means that the vectors are LD. Cannot be LI. And I'll just say S might span B. That's a maybe. That's a maybe. You have to actually check it by, how do you check if the vectors span B? Well, you lay them into the columns of a matrix, you do your number symbol business, and you hit it with EROs, okay? So in the case when you have too many vectors, so that could be 6 vectors in R5. Or that could be 10 vectors in M3 of R. So if I'm using the numbers over there that I know from those dimension values, and I'm just giving you something too big, right? If I give you 8 vectors in P6, the dimension of P6 is only 7. So if I gave you 8 vectors in P6, that's too many. You're getting it, right? So it's just a counting game. So if that happens, you're in the first column here, and you're looking at a set that's not LI. The second case, if I don't give you enough vectors, then S cannot span V. It's impossible. This is where you get the tall, skinny matrix. And when you have the tall, skinny matrix, guys, you are guaranteed to have a pivot go into those number symbols. It's going to crash into those number symbols, and that's bad. That means the vectors do not span V. And I'll just add here that S might be LI. It's a maybe. So again, you have to kind of check it. You have to kind of check it. You have to check that one. Okay, so that's the tall, skinny matrix, right? Where you have some number symbol here that picks up a pivot for sure. Something that looks like that. And what about when K equals N? I gave you the right number of vectors. Does that automatically make them a basis? I don't think so. What I said was that in the case when it's the correct number of vectors, you'll have a square matrix set up. And I said, well, yeah, they would be a basis as long as the determinant is not 0. But if the determinant is 0, then it's like double bad. Then it's like, so if this was a 0 here, then you would have a free variable and you would have a pivot in the far right column, both of which are bad. So in this case, S is both or neither. In those sort of that 4-part multiple choice option, it is either a spanning set and LI, this would be a basis, right? Or it messes up both questions. And this both case that's when the determinant of the matrix is not 0. And neither case is when the determinant of the matrix is 0. So you just take the determinant of your matrix and you get your answer based off of that. If and again, what is this A that I'm talking about? I'm just laying my vectors into the columns of that matrix. Kind of how that works. Just kind of making a little bit of sense. I hope so. I think, I think I will take 1 minute and say one thing about one of those problems over there, and then I'll call it good. I don't think I need to do anything else with this for right now. That's not okay, unless there's a question here. So get your flashcards going on your dimensions. I want you to learn those. I wanted to say one thing about one of these problems. Actually, so both 18 and 21, I think 21 is probably the better one to do because it's a little bit harder. This is for the homework for tonight. I'll just say a quick word on this. They're asking for a spanning set for the 3x3 matrices. So your vector space is M3 of R. I'm just gonna take 1 minute for this. Won't take long. And then it just says S is the matrices such that the elements in each row and each column add up to 0. And they ask you to find a spanning set. So what you need to do here, guys, is you need to figure out what is the form of such a matrix. What would a matrix in its general form using variables, what would it look like? Like if I told you that the first row has to add up to 0, I have 3 spots here. It's a 3x3. What would you fill out the first row with?
0, -1, 1.
Okay, that's specific. I want to do it with variables.
0.
I want to say that I can put anything here. Call it A. What would I put here? I would put B because the second entry does not have to be the negative of the first entry. It can be something else. But then what would I have to put here?
-4, A-.
The negative, I gotta make the whole row add up to 0. So if I've got something here and something here, then this has to be the negative of those two things added together.
Oh, yeah.
Right? I think I did work kind of like this last week. What about on the second row?
C, B.
Could I just do the A, the B, and the negative A plus B again? Careful. Does it say in the question that the rows have to be the same as each other? I don't think so. It just says the elements in each row and each column add up to 0, but there's nothing that says that the second row has to look anything like the first row. So I need to make sure that I bring in some new letters. So I bring in a C and a D, and then I bring in a negative of C plus D. With me? This is the hard part of the problem, is just getting the form right. And then the columns, it also tells us that the columns have to add up to 0. So if I've got an A and a C here, then to make that first column add up to 0, I gotta cancel out the A plus C with a negative. I do the same thing in the bottom middle. And then the bottom right corner just has to be A plus B plus C plus D again. This is the most general way of doing it. Okay, using letters. How many variables am I going to be busting out right here? 4 of them, right? I got A, I got B, I got C, and I got D. That means your spanning set should have 4 vectors in it, and you're going to make your list. So this is a 3-step process. Write down the general form of your vectors, bust out the variables, and then make your list. And just in case you're wondering, when you make that list, you're actually writing down a basis, just to tie it in with what we just talked about. You're actually writing down a basis for this subspace S, which is a 4-dimensional subspace of something that was actually 9-dimensional as a big universe, right? So just going back to the dimension is really kind of the size of the vector space that you're working with. So this is relatively small compared to the universe it's sitting inside of, but you're going to be writing down 4 spanning set vectors for problem 21. Does that make sense? That's how you do it. Takes a little practice to get used to writing down the general form of a vector in these vector spaces. But guys, I'll be around to help. If you have more questions on the homework for tonight, stop by my office hours today or shoot me an email and I will do my best. Thanks for being here. And I will see you again on Thursday. We might just get close to finishing chapter 4. Pretty amazing.
That's not your, like that's your.
I